The fifth lecture on Legendre differential equation. In the earlier lecture, we have considered the generating function and found the basic recurrence relation involving the Legendre polynomial and its derivative. Today, our point of discussion is the orthogonality of Legendre polynomial. Before going to the orthogonality of Legendre differential equation, let me first explain what do we mean by orthogonality. In three-dimensional space, if we have two vectors like this, ei cap ai, where I is equal to 1 to n, and b vector then we define their dot product a dot b is equal to summation over ij ai bj ei dot ej. Due to the orthogonality of the Cartesian component, this is delta ij, so we write it I is equal to 1 to 3 ai bi. If this is equal to 0, we call A and B are orthogonal. That means two vectors are perpendicular to each other. We may define vectors in a more than one dimensional space. Sorry, these were three. For three-dimensional space, these were three. In n-dimensional space, in ND space, we define the vector A as summation over ei ai I is equal to 1 to n. For God's sake, do not try to visualize the vector in an n-dimensional space where n is greater than 3. But this concept is found to be very useful in simplifying mathematics and which leads to correct results. So we define another vector likewise, and we call A dot B is equal to summation over I is equal to 1 to n ai bi. And again, if this is 0, then two vectors in n-dimensional space are orthogonal. Here, if n is finite, we say this is an n-dimensional vector, discrete n-dimensional vector. There may be occasion when n tends to infinity. In that case, we say two vectors to be infinite dimensional vectors, still in discrete infinite dimensional vector. Then n goes on increasing 1 2 3 4 up to infinity. Then we will have discrete infinite dimensional vectors, and if the dot product is 0, it is called orthogonal. Similarly, we may consider that a function, a well-behaved function between range a to b, x ranges from a to b. Say x is the variable, x ranges from a to b, and we have a well-behaved function f of x in this case. Then for each value of x, there is a value of fx. Since x can have infinite number of values between a and b, and the x values are continuous, then we may look it upon as the component of a vector. Here the vector is an infinite dimensional continuous vector. So if we have two functions f and g such that fx gx dx is 0, then f and g are said to be orthogonal. Then if this, then f and g of x are said to be orthogonal in interval a b. you see that the dimensionality was determined by the number of n's. Here this infinite dimensional vectors, and the range is specified by the value of the argument. So these two functions f and g are said to be orthogonal if they satisfy this condition. Sometimes it is found that the two functions f and g do not satisfy this relation, but one needs to have a weight factor. That is the integrating factor type behavior. The function f and g is not integrable, but when it is multiplied by a suitable function, then it becomes integrable. Then it is called the weight factor. In the case of Legendre polynomial, there is no need of a weight factor, because as we will see later that this function is already in integrable form. But for the other functions, as for example Legendre, Bessel, Hermite and Logger, we need to have a weight factor. Now coming to the orthogonal, with this concept that if we have two functions f and g which integrated from a to b satisfies this relation, we call them orthogonal, and sometimes one need to introduce an integrating factor. Now recall the Legendre polynomial. If the Legendre polynomial, we consider the Legendre polynomial of two different orders. That is, Legendre polynomial of order m satisfies this differential equation. Where m is an integer, and the nth order Legendre polynomial satisfies this equation. Here we have written Pn of x as equal to Pn, and the double derivative is denoted by double prime, and single derivative is denoted by this. We multiply the first relation by Pn and second relation by Pm and take their difference. So the first term will be now this term is we rewrite this as first thing. We can write it as if we differentiate this, first term is Pm double prime Pn, which is this. The second term is Pm prime Pn prime. When we differentiate it, it will be Pm prime Pn prime, which cancels, and the last term will be Pm Pn double prime. The prime was missing. We take it on the other side, so it is n square minus m square or we can write it as ddx of 1 minus x square if we integrate this over x between the range 0 minus 1 to plus 1, we get and on the right hand side we have you see the left hand side is simply this is equal to 0 because at x is equal to both the limits, this is 0 and this quantity is finite. So this is 0, and on the right hand side we will have n minus m n plus m plus 1 for m not equal to n. This is not equal to 0, this is not also 0 because these are 0 onwards positive quantities, they non-negative quantities, so which indicates that is equal to 0. So we see that Pm and Pn of x are orthogonal in the closed interval minus 1 to plus 1. Now coming to the fact that what happens to case when m is equal to n. This expression will not lead us to a conclusion. We will use the generating function expression. So we see that the Legendre polynomial of different orders are orthogonal. So we use the term like this: 1 minus 2xt plus t squared to the power minus 1. Minus 1, not half. So this is written as the product of two things. One is like this: t to the power m pm of x, m is equal to 0 to infinity, and other one is n is equal to 0 to infinity t to the power n pn of x. Now we integrate both the sides from limit. Now integrating, we get, you write this side first. So summation over mn t to the power m plus n integration pm pn dx from minus 1 to plus 1. Due to orthogonality, this term will contribute only when n is equal to m, and in which case we write n is equal to 0 to infinity t to the power 2n integration from minus 1 to plus 1 Pn square of x dx. This is the quantity that and on the right hand side we will have -1 to +1 dx 1 minus 2xt plus t square to the this. Now we consider the right hand side. So or summation over n is equal to 0 to infinity t to the power 2n this is the quantity. We introduce a variable, z as the variable which takes into account the denominator. So we write z is equal to 1 minus 2xt plus t square. So dz is equal to minus twice t dx, or dx is equal to minus 1 by 2t dz. For x is equal to minus 1, z will be 1 plus 2t plus t square, that is 1 plus t whole square. And for x is equal to plus 1, as t is less than 1. So this quantity becomes, if we interchange the limit, this minus sign will be accounted for. So it is 1 upon 2t 1 minus t to 1 plus t and we will have dz by z. So this is the value log z. This will be equal to, if we use the property of log function, this is equal to, this 2 cancels out, this is 1 upon t log of 1 plus t minus log of 1 minus t. We know the expansion of log of 1 by t. Log of 1 plus t is equal to t minus t square by factorial 2 plus t cube by 3 not factorial, and log of 1 minus t is equal to minus t. So if you write these things, for this part we will have t minus t square by 2 plus t cube by 3 minus t to the power 4 by 4. This is for this one, and this minus makes it plus. You see the even powers gets cancelled, so even powers gets cancelled. So we are left with 2 by t plus t cube by 3 plus t to the power 5 by 5. So this can be written as now comparing which this can be written in a compact form as two k plus 1. So that for k is equal to 0 first term, k is equal to 1 second term, and so on and so forth. So comparing this is an identity in T. So for T to the, if we compare the coefficient of T to the power 2n on the left and on the right, we find that Pn square x dx integrated from -1 to +1 is equal to 2 upon 2n plus 1. So if we consider both the things, that is the earlier we get that -1 to +1 pn dx is equal to 0 for for m not equal to n. We write both the relations together as summation integration from minus to infinity to plus infinity pm of x pn of x dx is equal to 2 upon 2n plus 1 delta mn. This is the orthonormality relation of the Legendre polynomial. Let me use this for the verification purpose of few low order cases, that is, we shall concentrate on case 1 and 2. So P1 is equal to x and P2 is equal to half into 3x square minus 1. We consider the integration 1, that is P1 square of x dx integrated from -1 to +1. This is x square dx from -1 to +1. So 1 by 3, and this is 1 minus of -1, that is +1. So 2 by 3, this is written by 2 into 1 plus 1. Then we consider 1, 2 as -1 to +1, P1 of x, P2 of x dx, this is equal to half from there, x 3x square minus 1 dx from -1 to +1. This is 0 as the integrand is odd. This is odd and integrated over a symmetric interval. And then coming to 2 part, this is 1 by 4, this is half square, and then we will have integration 3x square minus 1 dx from -1 to +1. Sorry, this is square. So this is 1 upon 4 integration from -1 to +1, 9x to the power 4 minus 6x to the power x square plus 1 dx. This integrand is even, so we write it as 2 times 0 to 2. So this becomes half, and then we will have 9 by 5 minus 6 by 3 plus 1. So this is half, this is 2, simply 2, so minus 1. So this is 9 by 5 minus 1, this is 4 2 into 5, so this is 2 by 5, this is 2 into 2 plus 1. So we see that the result is valid for n, n and m is equal to 1 and 2. You can verify the relation for still other combinations of m and n. That's all for the orthogonality of the Legendre polynomial. This orthogonality property enables one to expand any function, any well-behaved function in the range x plus minus 1. Consider a function which is well behaved in this region. Then, since the Legendre polynomial of all orders, that is starting from 0 order to infinite order, forms a complete set, we can expand f of x in terms of Legendre polynomial al PL of x, where L extends from 0 to infinity. This is the expansion coefficient. We can evaluate the expansion coefficient by multiplying both the sides by PL prime of x and integrate it from dx from minus 1 to plus 1. On the right hand side we will have summation over L is equal to 0 to infinity al PL of x, PL prime of x dx from minus 1 to plus 1. This is a delta function, so we will have summation over L L is equal to 0 to infinity. This part is 2 by 2 L prime plus 1 delta L prime. So this will be 2 times and when the sum is carried out, this becomes simply L prime is replaced by L. L will be replaced by L prime, so this is 2 by and sorry AL prime, AL is missing and this is AL prime, which gives you AL prime is equal to 2L prime plus 1 by 2 f of x PL prime of x dx from minus infinity to plus infinity. This is the expansion known as Fourier Legendre expansion. In Fourier series, we expanded the function satisfying Dirichlet's condition in terms of sine functions and cosine functions. Here we expand the series in terms of Legendre polynomial of all orders. And we need not to consider even function and odd functions separately, because Legendre polynomial of even order are even functions, while those of odd orders are odd functions. And the important concept that we have used is the completeness of the Legendre polynomial. That is, any function in this range minus 1 to plus 1 can be represented in terms of a Legendre function. A little bit on the completeness, we see that in two-dimensional Cartesian coordinate system, Cartesian coordinates I cap and j cap are sufficient to represent any vector in 2 dimensions. But when we introduce the z-axis, these two are not sufficient to represent all the vectors in 3-dimensional space. Then one need to add k cap. So in two-dimensional Cartesian space, I cap j cap forms a complete basis, while this fails to form a complete basis in 3 dimensions. Then I cap j cap k cap forms a complete basis in 3-dimensional space. That means any vector in 3 dimensions can be written as the combination of I cap, j cap and k cap with their suitable expansion coefficients like Px I cap, Vy j cap plus Vz k cap. Here Vx as if a0, Vy is a1, Vz is a2. That's this is the concept of completeness.